Good afternoon, and welcome to today's webinar, How to Avoid Unplanned Failure and Downtime on Vacuum Conveying Pumps. My name is Jim Colari. I'm the editorial director of Plastics Technology magazine. Our presenters today represent MachineSense and Novatech Incorporated. And it's my pleasure to turn the program over to our moderator this afternoon, John Kraft, who handles technical marketing for Novatech. John?
Hey, Jim. Thank you very, very much. We appreciate the opportunity that Plastics Technology affords us to talk about this important topic. We want you to know that we welcome your questions. During the presentation, please minimize the box on the right-hand side of your screen using the button at the top of the box. If you have a question, please open that box and type your question in this area on the right. At the end of each section of the presentation, we will respond to your written questions. Thank you very much. Our presenters are Jim Zinski and Fred Eichhorn. Jim Zinski joined MachineSense as President and Chief Operating Officer in March 2017. Prior to this appointment, and while serving as Senior Vice President, Product Technology at Novatech, he was an integral part of product development and market alignment for MachineSense. His responsibilities included strategic planning, product management, and R&D for pneumatic conveying and central product control lines, plus application authority for engineered systems, industry webinars, and resource training. Fred Eichhorn is the Electrical Controls Manager at Novatech. Fred has over 25 years experience in automation and electronics and manufacturing equipment. With his EE degree from the University of Maryland College Park and extensive experience in controls and power quality, Fred brings a dynamic level of expertise to the MachineSense production team and has been heavily involved in product development, testing, and manufacturing. Fred's previous experience includes custom machine design and building of industrial equipment in multiple industries. This is a lighthearted lighthearted look at a serious issue. Inadequate or inconsistent conveying performance can often lead to scenes like this, and the results are costly. First and foremost is unplanned and often hidden downtime in the form of starved machines, missed deliveries, lost profits, and angry bosses. It also leads to wasted time and lost productivity chasing conveying problems that can be difficult to diagnose and understand, but with help are very preventable. At the heart of the conveying system is often a positive displacement pump. Often this vital piece of equipment is forgotten until it fails. Once the blower has failed, similar chaos ensues as maintenance personnel have to scramble to get back the system online. Today, we'll look at frequent causes of premature blower damage and some methods to identify and correct these conditions so you can prevent costly pump failures and unplanned downtime. Jim, you want to start us off on this presentation?
Sure, John, thanks. First, let's put a perspective on the cost of failure as it relates to vacuum conveying pump failure. The top graphic illustrates a typical positive displacement pump replacement unit. The replacement cost for a PD pump can range from maybe $2,000 up to about $5,000 or more, depending on the blower model. These costs are typical for pumps commonly used for vacuum conveying pellets and regrind through a plastics plant using tubes that are typical 2 to 4 inches in diameter. The bottom graphic shows a vacuum pump assembly pulling resin from a remote material source to an injection mold machine. The cost of machine productivity uptime varies from plant to plant and from processor to processor, but in this example, we'll assume for 1 hour of machine uptime, it's worth $40. In numbers, the numbers may vary slightly or significantly depending on the nature of the processes. The time to remove the failed pump and install a new pump can also vary. If the replacement pump is in stock at your facility, a reasonable turnaround time for the repair can be as little as 2 hours. In terms of the cost of machine uptime, that adds $80 to the cost of the failed pump. If the pump's not in stock, the turnaround time for repair would be at least a day. In terms of machine uptime, that would add $960 to the cost of the failed pump, plus expedited freight charges, which can add up in a hurry. In this case, the cost of failure all in would range from around $2,000 on the low side to almost $6,000 on the high side. But most vacuum conveying pumps are supplying resin to more than a single machine. It's not uncommon for a vacuum pump to service from 5 to 10 machines. In some cases, depending on the application, a pump can service 15 or more machines. With multiple machines relying on a single pump to supply resin, the math related to the cost of failure is multiplied and can change dramatically. The bottom graphic now shows a vacuum pump assembly pulling plastic resin from a number of remote material sources to 10 injection molding machines. Multiplying the numbers in our example, if the replacement pump is in stock and repair is 2 hours, the machine downtime across the affected production cell now adds up to $800 plus the cost of the pump. If the pump's not in stock and it takes a day to repair, machine downtime now adds nearly $10,000 to the replacement pump cost. The net cost of failure across the 10 machines now ranges from about $3,000 all the way up to about $15,000 on the high side. Customer impacts can also be significant. Machine downtime can lead to late shipments and potential penalties associated with missed contract commitments. Your reputation as a reliable supplier can be put at risk, which can also jeopardize future business. These are steep prices to pay for failure of a single machine. That's why they illustrate that a vacuum pump is really considered the heart of your resin supply system. While it's not often thought of in these terms, in reality, vacuum conveying of resin to process machines really can be considered a valuable plant-wide utility for plastics processors. And what do we mean by that? Well, as we just saw in the example, and like most other utilities in your facility, an interruption in resin flow caused by pump downtime often affects multiple processes. So from that perspective, resin flow is as critical to plastics processors as water, power, and compressed air. Like power, arguably the most common utility, resin conveying principles are not necessarily intuitive, and symptoms are frequently misunderstood or even ignored. Resin conveying is more sensitive to system installation and setup than other utilities and requires more frequent maintenance. Redundancy is not widely implemented as a standard practice, so proper operation and maintenance is crucial to preventing downtime. As we illustrated in our example, resin supply interruption can quickly become costly when multiplied across production machines. Before we discuss common problems and the causes associated with conveying systems and vacuum pumps, it'll be helpful to understand some basic terminology. At the center of the graphic is a complete PD pump assembly. As the graphic illustrates below, air enters in through the top inlet on the top surface of the blower. You have two counter-rotating lobes in the center, and they take pockets of air that enters through that inlet and push them around the perimeter and push them through the outlet. Because the clearances are very, very tight, PD pumps are very efficient and capable of producing high vacuums. Coupled with the fact that these blowers are cost-effective compared to other technologies, they're commonly used and considered the workhorse in our industry. The graphic to the left shows the gear side or the gear end of the pump. Hidden behind the gears are ball bearings. Both types of components rely on proper lubrication for a proper operating life. The other sump on the right side of the graphic shows the drive end. Once again, you have bearings that rely on proper lubrication, and the slinger fingers installed to circulate the oil. In this case, the drive shaft often sees heavy side loads created by the belt that typically drives the rotating pump. Okay, so now that we know a bit about pump anatomy, we'll move ahead to common pump problems and their causes. This table summarizes common problems identified in a typical pump manufacturer's operation and maintenance manual. Some problems you may have observed in your own plant, like knocking or the sound of dragging inside of the pump, or you've seen loss of oil through seal leaks. These are tangible issues that you can see and you can hear. Other problems aren't so easy to identify, like excess temperature, lack of air volume, and excessive bearing or gear wear. Whether you can see these problems or whether they're invisible, the causes for these share a lot in common. These causes are highlighted in yellow in the table and summarized to the right. They're considered root causes because many of the other possible causes listed in the table are actually the end result of operating your pump under those listed. There's serious pump problems that can lead to premature failure, and they also share one very critical trait. They are preventable. These preventable root causes also share a common theme across the majority of industrial machinery. Surveys have shown over 50% of industrial breakdowns are due to improper lubrication. This includes under-lubrication, over-lubrication, and wrong lubrication, which means either the incorrect type or the lubrication failed. Lubrication and air filter issues, when combined, account for anywhere from 60 to 75% of machinery maintenance and repair for general industry. Once again, these problems are very preventable. We'll take a closer look at them in the slides that follow. Our initial focus will be on the lubrication issues. It may sound overly basic, but the first step is understanding the pump setup and proper lubrication. The breathers are located on the top surface near the back of the photo. As the blower heats up, the breather allows the expanding air to vent rather than stressing seals. The fill ports are located on the top near the front of the blower in the photo. The left side is the drive side, the right side is the gear side. Each has a different capacity requirement for filling, so if you're pre-measuring the oil, be sure to verify both amounts. Most pumps have oil sight glasses shown in the bottom photo. They allow you to fill the pump just by sight until the oil level reaches the center of that glass. When filling, it can take some time for the oil to find its level, so always pause briefly before checking the sight glass. Note the levels can only be checked when the pump is not operating. The most obvious and often quickest lubrication issue to do damage is an underfilled oil situation. If the pump is started and run when the oil is low, it will generate heat and the pump will experience metal wear. This eventually leads to additional complications with metal contaminants. They accelerate wear and they compromise oil seals. The damage to the gears can happen very, very quickly if the level is dangerously low. The gears wear and begin to fail, and you'll begin to hear a ticking sound or a knocking sound. That indicates the internal rotary lobes are clashing together due to backlash that's begun to affect the timing. End clearances can change, forcing the driven rotor into the end plates. Underfilled oil will also cause the bearings to begin to fail. As shown in the bottom photo, the ball bearings are exposed and they rely on a consistent supply of oil to maintain the lubrication film that's sufficient to prevent metal-to-metal contact. It's important to note pumps with damaged gears, bearings, or seals can be rebuilt, but only if the damage is caught early. The key is recognizing the problems before damage is done to the blower housing and to the blower lobes. A not so obvious lubrication issue, but still capable of doing damage, is an overfilled oil condition. Excessive operating temperature can occur when the pump is started and run with too much oil because the heat can't be dissipated effectively. This causes abnormal stress and wear of gears, bearings, and seals. This can cause surprisingly quick failure in extreme conditions. A pump manufacturer explained it to me this way. Operating a pump in a near with a near empty oil reservoir can lead to failure within a few hours or even less. But running a pump with a sump that's filled to the top can lead to failure in as little as several days. Once again, if the problems are caught early, before damage occurs to the pump's major components, it can be rebuilt. The final focus when it comes to lubrication relates to the type of maintenance of oil you use. PD pumps require industrial gear lubricant, not automotive oil. Check the pump manufacturer's recommendations for viscosity, additional requirements or restrictions for additives, seal compatibility requirements, and other enhanced properties that are designed to protect your pump. Synthetic oil is recommended because of the high heat of compression and temperatures in vacuum conveying. The maintenance interval for your oil depends on the operating temperature. The graph to the right shows synthetic oil operating life decreasing sharply as the pump air exhaust temperature rises above 220 degrees. Depending on application and so forth, PD pumps can operate commonly between 220 and 250 degrees Fahrenheit when fully loaded. So it's important to understand those operating conditions when you try to evaluate your pump's change cycle. Finally, as with other lubrication issues, and for many of the same reasons, using the wrong oil or oil that's failed from thermal breakdown or contamination will damage gears, bearings, and seals over time. So let's change our focus to air filtration, the other very common problem with industrial machinery. Operating a pump with poorly maintained filters can cause excessive operating temperatures. The elevated temperatures result from increased vacuum levels or starving air, which leads to a lack of cooling. The common theme is accelerated oil failure and gear and bearing damage. It can also cause discoloration of the pump exterior paint. Clogged or damaged filters can lead to fines being pulled through the filter media and into the pump. Inside the pump, the high temperatures will melt the fines and cause them to accumulate on the housing and on the rotary lobes. In extreme cases, the residue can score or gall interior surfaces or even cause the pump to seize. The final problem with poor filter maintenance is reduced and inconsistent conveying performance. The added vacuum load can reduce the pump's ability to lift and carry material through the line, causing intermittent slugging, line plugs, and reduced throughput. These conveying problems can lead to downtime, missed part quotas, scrap parts, and other hidden costs. Before we finish up with the problems, we're going to focus a little bit on system operating conditions. Operating the system in an over vacuum condition, as we just mentioned, creates unstable conveying conditions and can reduce conveying rates, and that creates excess heat and all of its related problems with the blower. It can also cause rotary lobe damage either by hitting the housing or through interlobe contact. High ambient or high inlet temperatures also stress the blower. These can be the result of conveying heated materials or from inadequate ventilation near and around the pump. It's important to remember that you can prevent over vacuum conditions relatively easily. Always use an adjustable pickup device at your material source. When high vacuum occurs regularly, adjust this pickup to allow more air and less material into the conveying line. Most receivers include a filter screen to separate material from the conveying air. When problems seem to be intermittent with vacuum, check related receiver screens for plugging. Finally, most conveying systems have a central dust collector to separate the majority of the fines before they reach the pump. It's normal for their internal filters to accumulate dust over time, and they will require cleaning to maintain normal conveying system performance.
Okay, Jim, it's time to see if we have any questions. And while we're waiting for questions, a couple of things dawned on me. I know you covered costs related to pump downtime, but it seems to me that there's also a problem with the material that's in process, that's in the machines waiting to be processed, And when processing stopped, the packaging of the final product also stops. So there are costs from the beginning to the end of the line, not just with the pump.
Yeah, absolutely. Yeah, so you would kind of consider those to be part of the machine uptime or productivity number. And again, depending on the end product and the process involved, it can range dramatically. We used $48 an hour, but as I said, it can be lower, it can be much higher.
Yeah, and also as far as catching pump damage early, just by hearing a noise, I would think that's pretty difficult due to the noise from other pumps and machinery. So I guess we're going to talk about how to get around that in the future here.
Yep, we will. Absolutely.
Okay, I'm not really seeing any questions yet, so let's move on with the next session of the presentation.
So these are challenging times for production and maintenance teams. Production has focused on improving their process. Maintenance teams are being asked to troubleshoot and fix more problems with less funding. They need to be more productive. In speaking with customers around North America and Europe, we've been hearing that declining maintenance budgets are due to two big contributors. Economic downturns have resulted in company-wide budget constraints, and failed maintenance programs have resulted in future funding being denied. A 2017 Plant Services Magazine study saw that 41% cited budget constraints and 40% cited poor program execution as obstacles limiting their maintenance initiatives. You're not alone. It's happening to everyone. It's not new. It's been happening for years. Seasoned maintenance professionals are retiring. A major skills gap is occurring. With these specialists retiring, expert institutional knowledge is being lost. In addition, new technology has been brought to new equipment, which are becoming more complicated and sophisticated. Many machines are not intuitive. Most users and manuals are now no longer tech manuals. They are now just operating manuals. We're all having to do more with less. Some traditional diagnostic tools that have helped us are mostly for screening and diagnosing. They can provide the current conditions of the equipment, but they really, the cons are they don't really have data records for diagnosing conveying performance and are not always compatible with existing controls. Vibration analyzers are a time-tested practice and can provide key insight of machine health, but these devices are typically on-spot and capture a single point in time. They require resources typically and time to collect data, and often require training or third-party expertise. You must record or upload data for future comparisons and troubleshooting, which is key for finding root cause analysis. Technology is reshaping our ability to monitor and analyze. The industrial Internet of Things has allowed sensor data to become more accessible. Data analytics are becoming more advanced, and historical trends are automatically captured. 24/7 machine monitoring is possible. It captures varying conditionings for improved analytic results. It is easy to access and understand results via app or web page. Automated reporting via email or SMS text messages are included and simplifying information feedback to the people who need it most. MachineSense Vacuum Pump Analyzer takes advantage of these Internet of Things benefits. This is achieved by continuous machine monitoring and provides prospective feedback and helps with root cause analysis. trending and early detection of component deterioration, even under changing loads. Again, as I mentioned, really critical for helping to understand the equipment through time. Wireless data hubs included, which allows for wireless connection to your sensors and to your internet. PumpSense component analyzer is an easy and powerful magnetic mount sensor. It measures vibration and ambient operating conditions. A vacuum sensor with built-in power supply is also included. Therefore, it does not require any maintenance or battery replacement, typical with other types of sensors. These sensors measure, as just mentioned, temperatures and vibration, vacuum, ambient temperature, ambient pressures. These are all critical in understanding and getting a true representation of the equipment and its conditions. These combined with the analytics in order to determine filter condition. We have check oil analytics that tell you if your oil level is low or your viscosity is low. Blower bearing health, vacuum trends, and operating health, all of these trends and metrics to help understand proper utilization of your pump in your system. The sensor, a vacuum pump analyzer works like this. The sensor data transmits wirelessly to a data hub. It is then sent through a customer supplied network router to a cloud-based servers running powerful analytics software. This is the Crystal Ball software. MachineSense's patent-pending analytic algorithms tracks and compares the collected data against an established baseline to determine overall pump or blower health and alerts you to changes in performance, allowing you to accurately diagnose problems before they happen. Our easy-to-use Crystal Ball condition monitoring software is accessible through a web browser and easy-to-navigate mobile app, allowing you to view real-time machine conditions anytime, anywhere, from any desktop, computer, laptop, tablet, or phone with an internet connection. Valuable operating metrics are delivered through easy-to-understand dashboards and trend lines. If a machine or component reaches a yellow warning state, actionable maintenance advice is delivered to assigned technicians via email or text messages in advance of machine or component failure. It's super simple to install right out of the box. First, check the belts, air filter, and oil to ensure normal operating conditions of your pump and adjust if it is needed. Second, install the sensors on the pump itself. Third, install the data hub within 15 feet of the pump and plug in the 115-volt outlet. Fourth, we establish a network connection via wired Ethernet or Wi-Fi and using the Wi-Figurator app. Now you'll be ready to access the vacuum pump analyzer through Crystal Ball, the machine monitoring website. Some more details on the sensor mounting. It's quite simple and straightforward. Mount control box on the pump assembly or a nearby surface. Step 2, place the sensor securely on the pump with the magnetic mount. 3, install a T-tap on the vacuum gauge and connect a vacuum hose. And 4th, connect the control to the appropriate power source, typically from the pump control itself. And it comes in 115 or 24-volt DC to help facilitate that. This, when you get to the Crystal Ball software, this would be, this is your dashboard overview screen. The vacuum pump analyzer's dashboard overview screen is the home page when you would launch to monitor your pump. A user settable name for the selected pump will appear in the center of the screen as shown by arrow 1. Use this page to view operating analytic gauges for your pump and to access predictive analytic trends to diagnose pump bearing, oil, and filter health status. The dashboard also displays ambient operating conditions and the network connection status for the pump sensors. So conditions at a glance, we have green, yellow, and red conditions on our gauges. Green obviously indicates good condition in the case that sensor installation dashboard is valid data. The yellow indicator is indicating a deteriorating condition and requires attention. And the red, of course, indicates a poor condition that must be corrected to avoid accelerated component failure. This obviously could be leading to unplanned downtime. Another possible case is invalid data in the case of a sensor installation, as shown in item 3, arrow 3 in the red vibration. So we were just talking about the sensor installation. The sensor installation, as you can see here, it shows that the sensor is mounted properly. You're getting enough vibration. Our analytics ensure that a sufficient location and mounting have been made, and you'll see that with the green gauge. If not, it'll be red and you'll have to remount. The pump on time is a 24-hour gauge that just gives you a good indication of how much the pump is running during the last 24 hours. The pump utilization under load is a gauge for the last 24 hours. This gives us an indication of how much pump capacity is being used on your system, how often the pump is running and doing work. The blower health dashboard is the heart of the machine. That's showing us our blower's health condition. This is particularly relating to the drive bearing and rotational balance with trending over time. The oil check dashboard indicates the condition of the oil, low level or poor viscosity, and of course helping prevent the pump from operating in these conditions is crucial to extended life. The filter status dashboard indicates the condition of the filter with trending over time. The vacuum breaker valve creates an idle mode, which during this idle mode, the pump is operating at a no load vacuum level. Therefore, the vacuum of the level in the system is an indication of the amount of vacuum being lost across the filter and gives us a very good indication of the filter condition and its status. The operating vacuum 24-hour gauge is one of the most important gauges. It gives us a real good overall system health and how it is operating. Obviously, operations in the red zone need to be corrected immediately and can result in immediate and premature failure of the blower. Operating in the yellow should be avoided and can be indications of over vacuuming the pump blower system and issues with setup of the vacuum system. Everything should be in the green. The gauge for vacuum frequency is a 10-minute gauge, and this is more like a real-time gauge. So it's like seeing the local vacuum gauge on the pump remotely. It gives us the ability to see this remotely and get an indication of how that pump is currently running. The vacuum pattern gauge is a 4-hour gauge. These give you important insight on how the pump and the conveying system is operating during this time. Shifts in these patterns can provide an early indication of changing conveying conditions, especially with material supply issues like plug lines, vacuum leaks, clogged filters, can also be indicated by this. The next slide shows an example of how this gauge can be helpful. So, for example, the vacuum pattern gauge on the left shows a hypothetical normal operating pattern for a given conveying system. Dramatic shifts shown here are an early indication of change in conveying performance. In the center dashboard gauge, the vacuum pattern has shifted, indicating less idle time and more low vacuum operating time. This is frequently a signal to check for an empty material supplies or to check for possible vacuum leaks. So our system is operating below expected vacuum. Comparing the normal gauge on the left to the gauge on the far right, the vacuum pattern has shifted again, indicating the pump is drawing a high vacuum more often than usual. This is a signal to check for over vacuum conditions, such as clogged vacuum receiver filters or a material pickup device that's overfeeding the conveying line and stressing the system. So you can see how these three patterns were able to help diagnose your system conditions, these changes in patterns. One of the nice things about the vacuum pump analyzer is its trend data and maintenance advice. This is your expert. The analytics included with this system can provide maintenance advice whenever you're in yellow or red conditions with easy, understandable, actionable maintenance procedures and steps to help prevent failure and to extend your machine life. In addition to the nice dashboards, gauges, and trends, Crystal Ball software will provide alerts and maintenance suggestions. These will be sent via text and/or email to assigned personnel. Users selected in the software, these modes of communications can be checked and changed in the user profile. It's a great tool for maintenance staff in alerting them of conditions and suggestive maintenance in the summary pages. So here's an indication of the summaries that I was referring to, and with the different gauges, what the actionable alert issues can be, and the maintenance suggestion follow-ups. So it's not just telling you that there's a problem, it's helping to point you in a direction of a solution. So this trend is an example of a filter status dashboard. The blue line is the trending of the vacuum level, and you can see it crossing through the yellow and then onto the red. So these thresholds that trigger these notifications can be sent to technicians when there's an issue, and these baselines can be used for notifying you of a component or machine is approaching a fault. This trend represents the blower health dashboard. This one is again, you can see it's blower health is deteriorating, getting to a yellow area where we might need to start to look at doing some type of maintenance, and then just getting towards the red. There may be indications of that that there may be some type of impending failure on your blower, and hopefully you can catch this and prevent failure before it becomes an absolutely critical downtime situation.
Thanks, Fred. Before we finish up, I'm going to circle back to the start. We've seen vacuum pumps are vital to plastics manufacturing processes. When they stop, material stops, parts production stops, and money stops. We've identified key vacuum pump problems. and system operating conditions that lead to premature damage and unplanned or hidden downtime. The vacuum pump analyzer provides a new powerful tool to help processors get the most out of their vacuum pump and their conveying system. With it, you can identify deteriorating conditions as they happen with continuous 24/7 monitoring. You get real-time maintenance alerts sent via email and text. You can perform maintenance based on actual machine condition. It's easy to use, easy to understand, and no specialized training or expertise is needed. And best of all, it'll help you avoid unplanned failure and downtime on vacuum conveying pumps.
Okay, it's time for some questions, Jim and Fred. This sounds pretty exciting in that it sounds like this is the first time there's been a 24/7, 365 way of monitoring the condition of vacuum pumps for a variety of conditions. Is that true, Jim?
It is, John. One of the reasons we can do it, it usually takes a tremendous amount of data to be able to do that, and it's typically not practical to take that data and have to store it, transfer it, and so forth. But with some patented analytic techniques or patent pending analytic techniques, our sampling techniques allow us to take this data and normalize it over time and provide the real-time analysis that provides up-to-date machine condition.
Okay, one of the questions we have here is how many sensors can be on a typical system, and can sensors be added at a further time if needed?
Yes, absolutely. So there's really no limit to the number of sensors. It's all governed by really the number of devices that you have to monitor. We simply have to make sure that we have enough data hubs to collect the data and transfer it to our servers. Yeah.
Now, if I understand this right, though, there's really only one sensor required per pump. Is that right?
There's one vacuum pump analyzer package required.
Okay.
That includes a vibration sensor, component sensor, and it also includes a vacuum sensor.
Okay,
So,
gotcha.
if you'd like to try it out on one unit just to see how it works, you can always add sensors at any time. They would simply be added to your account, and they would be displayed with any other assets that you had previously purchased. The other thing is, if you buy the single pump and a single data hub, you can add a second pump to that single data hub. So you can actually have two vacuum pump analyzers working through one data hub. So that will also save some investment cost.
Okay. And go ahead. Fred.
There's also, actually, I was just going to say, there is also, following up on that, there is questions regarding costs of the vacuum pump analyzer.
Okay.
So that ranges.
Yeah. So if you, the products are on our website and the prices are listed there. For a pump with a data hub, the price is $750. For a vacuum pump analyzer without data hub, it's $550. You can also buy a 2-pump package that'll have one data hub and sensors for 2 pumps, and that's $999. So you get monitor 2 pumps for less than $1,000.
Okay, and there's another question here. It says, is this technology available for other machine applications, for instance, extruders?
It will be. So at this point in time, we have MachineSense offers a power analyzer package that can be used to monitor power quality as well as provide diagnostics on specific components such as heater banks and large drive motors and so forth, VFDs and the like. We will be releasing individual component sensors that can be used for say defining trends on components for machines. So we don't anticipate having an extruder, a complete package for one extruder. I think customers or processors that would want to monitor could add the sensors to the components that are critical and go about beginning to analyze the trends accordingly.
Okay. All right. Go ahead, Fred.
I was just going to follow up with regards to the question that a person was asking as well about the price for monitoring the data. So included with the vacuum pump analyzer, you get 6 months of free data trending and analyzing using the product. And then after that, there is a subscription pricing. You want to elaborate that more on that, Jim?
Sure. It's $15 per month, billed annually. So that's $180 per year per pump. At this point, it's the same for the Power Analyzer product as well. We do anticipate for those situations where we have a large number of sensors, we will add into our subscription plan site license type of programs to actually put a cap on the cost of that data and subscription for end users.
Okay, well, all that sounds very interesting. Please remember that you can contact Fred Eichhorn directly or Jim directly at the email and phone numbers that are listed. And with that being said, I'm going to turn this back over to Jim Colleri. Thank you very much.
Thank you, John. On behalf of today's presenters from MachineSense and Novatech and Plastics Technology, I'd like to thank you for joining us today. This webinar was recorded, and soon we will be emailing you a link pointing to the recorded version. Please take the liberty to listen to this webinar again or forward the link to any of your colleagues who could not join us today. Thanks again for joining us. Goodbye.